Hello students, in today's class we learn about trigonometry. Trigonometry deals with ratios of sides of a right angle triangle with respect to certain angles. It has been used since ancient times. Earlier astronomers used to take the help of trigonometry to find the distance between Sun, Earth and other stars. Even today we continue to use trigonometry in modern physical technologies, in physical sciences, and everywhere. Most of our studies in class 10th will be restricted to acute angles for trigonometric functions. We will be defining trigonometric functions in terms of sides of a right angle triangle, and once we are over that, we will go for finding values of acute angles of trigonometric functions. These values will be restricted to acute angles in class 10th, but it does not mean that these values stand only for acute angles. They also are present for other angles about which you study in higher classes. After finding certain values for 0, 30, 45, 60 and 90, we will be using some trigonometric identities to solve questions. So let's get started with understanding sides of a right angle triangle. Let us consider a right angle triangle PQR, right angled at Q. In a right angle triangle, the side opposite to the right angle is always the largest side and is called the hypotenuse. We also know that apart from hypotenuse, the two other sides of the right angle triangle are perpendicular and base, and they are related to each other as h square is equal to b square plus b square by what is known as Pythagoras theorem. However, although hypotenuse is always fixed, perpendicular and base depends on the angle that we are considering or the orientation in which the triangle has been kept. So suppose this same triangle is now slightly rotated and it gives us PQR like this. Then although hypotenuse remains same, we can clearly see RQ is now the perpendicular and PQ is the base. So what we say is that perpendicular and base depend on angle of view. In this case we are viewing from angle R, whereas in this case we are viewing from angle P. Based on this, we will define 6 trigonometric ratios, which are ratios of these sides of the triangle, which is perpendicular, base and hypotenuse. However, we will not take perpendicular and base in the classical sense. We will take them in sense of the angle considered. So if my angle R is considered as theta, then the side opposite to theta is considered as perpendicular, and the side adjacent to theta is considered as base. In the same triangle, if I draw like this and I say this is my theta, then obviously perpendicular and base get altered. So we clearly now see that perpendicular and base will depend upon the angle of view or the angle which is taken into considerations. Based on that, now we will define 6 trigonometric functions or ratios. The trigonometric functions are written as sine of an angle, which primarily in short we write as sine theta. We should remember that sine and theta are not two components. It is not something like sine has been multiplied with theta. Sine theta is a single component, and only when they are combined we get a certain value or a certain ratio. let us again come back to the triangle PQR, right angle at Q, and take angle R as theta. So this side is the side opposite to theta. In short, I'll just write opposite, and this is the side adjacent to theta, whereas hypotenuse obviously remains PR. So we start defining our trigonometric functions with sine theta. Sine theta is equal to opposite upon hypotenuse. And since side opposite to theta is the perpendicular, we can also write in short P by H. The second trigonometric function we define is cos theta, which is basically short of cosine, but it is written normally as cos theta only. Cos theta is the side adjacent to theta upon hypotenuse. So this will be base upon hypotenuse. And the third trigonometric function is called the tangent of theta or tan theta, which is opposite upon adjacent. So there is no hypotenuse in this. Opposite is, as we know, perpendicular, and adjacent is base. These are the three primary trigonometric functions: sine, cos, and tan. Now very quickly we see something remarkable about tan, something that can relate sine and cos with it. So what is this? We just now devised tan theta as perpendicular upon base. So what happens if I divide both numerator and denominator by hypotenuse? What will I get? Perpendicular upon hypotenuse, as we see here, is sine theta, and base upon hypotenuse, as we see here, is cos theta. So I can say that tan theta is also equal to sine theta upon cos theta. This is something we may use later on in solving many questions in trigonometry. So first stage, we define the three primary trigonometric functions, and then we come to three more, which are nothing but the reciprocal of these three. So to do that, we will again draw the right angle triangle PQR, right angle at Q, and start defining the reciprocals. This was our angle theta, Q 90 degrees, and P. The next or the fourth is cotangent theta, but pronounced as or written as cot theta. This is basically adjacent upon opposite. As we can see here, it is the reciprocal of tan theta. So I can also say that cot theta is actually equal to 1 upon tan theta. The fifth trigonometric function is secant theta, or commonly written as sec theta. It has hypotenuse in its numerator and side adjacent to theta in the denominator. So h upon b is equal to the reciprocal of cos theta. The last trigonometric ratio is the reciprocal of sine theta, called cosecant theta, but mostly pronounced and written as cosec theta. Cosec theta also has hypotenuse in the numerator, and the side opposite to theta is the denominator. So it is equal to h upon p, which means 1 upon sine theta. So we have now defined all the all the six trigonometric functions, and we can summarize these definitions as here. Clearly, the first one is sine theta, which is equal to perpendicular upon hypotenuse. The second one is cos theta, which is base upon hypotenuse. And the third is tan theta, which is perpendicular upon base. We also learned about tan theta, that tan theta is also equal to sin theta by cos theta, and it is also the reciprocal of cot theta. The fourth one is cot theta, which is base upon perpendicular, and since it is the reciprocal of tan, it also means it will be cos theta by sin theta, or 1 by tan theta. The fifth is sec theta, which is equal to hypotenuse upon base, or 1 upon cos theta. And last is cosec theta, hypotenuse upon perpendicular, or 1 upon sin theta. So after writing these, we will modify sin cos also to know that they are reciprocals of cosec theta and sec theta respectively. All these functions are actually only ratios. They do not indicate any real value of perpendicular or hypotenuse. What I mean by this is, suppose we are given that sin theta is equal to 3 upon 7, and we also know that sin theta is equal to perpendicular upon hypotenuse. Does it mean that perpendicular is 3? The answer is no. Why so? Because it is a ratio. When I am writing 3 upon 7, it could also be 9 upon 21, it could also be 12 upon 28, and so on. So since it's also only a ratio, that means it has been reduced to its lowest term. So in this case, what should we take the value of perpendicular and hypotenuse? It's very crucial. So what we do is, if we are given that sin theta is equal to 3 upon 7, we say perpendicular is some multiple of 3 and hypotenuse is some multiple of 7. It could be 1 also, it could be 2 also, or it could be any real number. And since p square plus b square is equal to h square, this relationship helps us to find base. So here 9k square plus b square is equal to 49k square, gives me b square is equal to 40k square, or b is equal to 40 root 40k. Root 40 is 4 into 10, so I can write it as 2 root 10 into k. So now what I see is that in the given question, I have perpendicular, I have hypotenuse, and I have found out base. Therefore, I can write all possible trigonometric ratios. For example, I can write cos theta. Cos theta is base upon hypotenuse. So from what we have found out, 2 root 10k upon 7k. So we have 2 root 10 upon 7. I can write tan theta, which is perpendicular upon base. So 3k upon 2 root 10k, which gives me 3 upon 2 root 10. In the preliminary first exercise of the chapter, we will be doing questions like this, where one of the trigonometric functions will be given to you, and you will be asked to find certain values which relate to finding other trigonometric functions. So what we remember is that are a couple of things, that this is a ratio and this is not an absolute value, so we take it as a multiple of something, and of course we will be continuously using Pythagoras theorem to find the third side when any two sides are given. Of course, we also have to remember all trigonometric ratios, and one of the short ways of doing it is, which has been in use from long time, even to the time when I was a student. So what we wrote in that time, sine, cos, tan, as we know the numerator is p, B. Opposite we will say same, Pandit, Badri, Prasad. And then we had upon H, upon B, or HHB we will say Har, Bole. It's a short way of remembering, but we can remember without this also, that would be great. But what is important, we should remember sine, cos, tan. Once we know sine, we know that 1 upon sine is cosec. From cos I can get sec, and from tan I can get cot. In our next class we will be doing questions related to one trigonometric function being given and other trigonometric functions or such expressions being determined with that. Thank you, all the best.